Hello friends, in this tutorial we shall study the bit array rate for multi-user spread spectrum system, that is a DSSS MU BPSK system over a frequency selective fading channel, which we are going to model as a Rayleigh fading channel. So as we see, we have multiple users transmitting data to a common source, that is a common destination, and these multiple sources have been labeled as 1 to k. So there are k number of users, and each user over here is the data corresponding to each user is spread using DSSS spreading code, which is further modulated and combined and passed through the channel. The combiner in our case for this the spread signals of these k users is going to be a simple summer, as we shall see, and the channel which we are going to use is going to be the Rayleigh fading frequency selective channel. At the receiver we have the AWGN noise, and after performing MMSE equalization we despread the signal using the spreading code of that user whose signal we wish to receive or decode. Of course, this block you may be familiar with. It's nothing but taking the inner product of the desired user spreading code with the incoming received signal and summing over all the elements of the result. We further pass this through the BPSK demodulator in order to detect or decode the bits of the user that we wish to know, the signal of the user that we wish to decode. So once again, remember that the modulating data source will emit a binary stream of bits. For example, we could have, let's say, if bit 1, that is a binary bit 1 is sent, then this is going to be mapped to a bipolar signal level. Let's say some other user wants to transmit a 0, then the bipolar representation of this, let's say, could be -1. The spreading code generator will have some spreading code length. Let's say the length is equal to 4. Then in that case we might have some spreading sequence, for example, which may be once again represented in bipolar terms, and this multiplication is nothing but the multiplication of this bipolar input signal to each of these bipolar entities of the spreading code. So similarly, this will be multiplied by some other unique spreading code which may be orthogonal to the spreading code of the first user. The examples of such codes we have already seen. These different unique codes, orthogonal codes with good autocorrelation and cross correlation properties. For instance, we could have Walsh-Hadamard codes, and therefore these code sequences could be rows corresponding to the Hadamard matrix which we have generated previously in our tutorials where we showed the MATLAB code for its generation. As I said, this combiner in our case will be simply summing up the resultant spread signal, that is after multiplication, what we get over here. So we, depending on the number of users, we will sum up the corresponding elements in order to get the composite signal. So let's proceed and see as to what is the concept of multi-user communication. So in our system model we assume downlink transmission. So this is an important point that needs to be noted. We are not analyzing this system or not evaluating its performance for uplink, I will come to the problems involved for uplink performance evaluation in a short while, but as of now please note that we are going to do downlink performance evaluation. So we have a base station and we could have multiple users from 1 to capital K as was shown before. User small k is some arbitrary user. It is assumed that each of these users signals at the receiver will be due to multipath effects of the signal which has been transmitted from the base station. For example, user k over here is a direct path, line of sight path with channel gain A and delay tau naught, and then it has two other paths. Similarly, user 1 has a direct line of sight path and another reflected path. So in general we could change the parameters, that is the channel gain, the delay, etc., and we could model the entire system. So we'll see what kind of model we have or what are the parameters that we have chosen for simulation, so that we'll see shortly. But as was explained in the previous tutorial as well, for each user we could model this phenomenon in terms of linear filter with tap gains corresponding to the channel gains and tap delays corresponding to the path delays. So this is a mathematical model for the multipath fading due to each path for a given user. And for a mobile channel, as we know, we can, if the number of paths are sufficient enough, which is an assumption of course in this case, then we could model this the amplitudes, or rather the multipath, in terms of Rayleigh distributed amplitudes which have uniform phase from 0 to 2 pi. So that is what we are going to do as we proceed. The 2 points which I had also made in the last tutorial, that is the detection errors, even though we have the right spreading code, could occur due to channel impairments and noise, which is the intention or objective of this tutorial. And so we need to find out the probability of error. And another thing is that good autocorrelation property of the spreading code, and in this case of course the autocorrelation property can be used in order to counter the multipath fading, and the good cross correlation properties are useful in a multi-user scenario. So let us have a look at the MATLAB code that implements the system model just described. We have a certain number of samples which is nothing but a number of bits that we need to transmit. We are going to run this entire simulation over 200 iterations in as Monte Carlo simulations basically. So we have a length of the spreading code equal to 4. We assume that we have 3 users, so it's a pretty simple case. We set the EB by N naught range. In line number 19 we have and 20 we initialize the variables that we will use to store the average probability of error and the combined signal, spread signal due to the 3 users respectively. We assume a exponential power delay profile, which is not uncommon in mobile communication systems. So we set the delay parameter to a typical value of 1.2, and we choose the number of multipaths to be 4 for all users. So this is a simplistic assumption. You could change this and explore in order to see how the performance evaluation looks like. We choose the number of rather the delay corresponding to the multipaths, and we generate the exponential power delay profile in line number 25 using the parameters that is the decay parameter and the delay. we find the amplitude for this power delay profile, which we use in order to generate the impulse response subsequently. The Rayleigh distributed random variables are generated in line number 27, which is nothing but a complex Gaussian entity. As you can see, the impulse response of the channel is nothing but this complex Gaussian quantity multiplied by the PDP amplitude, which is exponentially decaying. So this is a standard procedure in order to generate the impulse response of a Rayleigh fading frequency selective channel. The channel power is found from this impulse response because we need to normalize the impulse response in 30, and we do that in line number 32, and you could then plot this impulse response versus the delay in order to look how it looks, how it is like. We had done this in the previous tutorial, so that's why I have not shown the plot over here. The next part of the code, the MATLAB code, is to generate the Hadamard matrix, the rows of which correspond to unique orthogonal spreading codes. So that is in line number 39, and then we use a for loop in order to generate data, random data, which will have a length that we have already chosen before, that is in line number 14, as you can see, and we spread the data by finding the inner product, as I said. But what is to be noted in line number 42 is that since this is a loop and it runs over the given number of users, for each user this variable AA will keep changing, and so what we are doing is we are choosing a given row of data from the that is from this line number 41, which is nothing but a matrix comprising of rows corresponding to users data. So we choose the given row for a given user. In this case there are 3 users, so we choose a given row and multiply it with a row of the Hadamard matrix, which again is unique. So for 3 users in this case, we will have 3 different rows of the input data matrix and 3 different rows of the Hadamard matrix, which we have found in line number 31. So once this inner product is found, we store it in this variable, and then we run the loop again for the next iteration for the next user. So like this, in this manner we complete for this case 3 iterations, and we get the composite signal, which is the addition of the 3 spread data sequences. We store the length of this combined signal, which will be the length of the individual spread signal itself, because we are adding up the 3, so the length doesn't change as such. We calculate the power of the combined composite multiple user spread spectrum signal in line number 47, because we need to use it in order to scale the power accordingly. And what we notice is that we divide this entire power by the length of the transmit data. So basically what we are doing in this code is that we are assuming that the available transmit power is split into the 3, that is 3 users are sharing the available power. So we have uniform power allocation scheme. We calculate the noise in this if else part of the code, but before that we convert the EB by N naught to linear scale, and then we convolve the combined multi-user signal with the impulse response that we had generated in line number 32. So this takes care of the frequency selective nature of the channel, and we generate noise depending on whether we are plotting the EB by N naught for the BER or whether we are plotting the SNR. So the difference, as was pointed out in the previous tutorial, is that when we do it with EB by N naught, since the same energy per chip in the that is the original signal is spread when we carry out the spreading process, so we need to do this scaling. However, for SNR the power remains same per chip with or without spreading, so this square root length code term doesn't figure over here. However, we shall plot the results against EB by N naught. The received data is nothing but the addition of the transmitted data from 55 plus noise that is generated, and we calculate the variance of the noise because we need to use this parameter for the MMSE equalizer which follows. The MMSE equalizer is LC plus 1 tap equalizer, the code of which is shown over here, and what we see is that we finally use this equalizer in order to mitigate the effects of frequency selective fading, and once that is done we store the signal and we use the mathematical operations that I had already discussed in the previous tutorial. So this part of the code from 74 to I think we have 97 follows the same procedure as we had discussed in the single user case in the last tutorial, so I am not repeating this part. And the decoded signal after despreading with the code of the desired user, in this case we are using as you can see the code of the second user, so that is what is to be decoded in line number 95. So once we do that, we find out the error, we sum it up and we average in line number 103. So the idea now is to see as to what kind of BER performance a multi-user, a 3-user in this case system, spread spectrum system yields in the presence of a frequency selective channel. So what we see here is that we have the performance of BPSK system without spreading in a Rayleigh faded channel, which is given by this circle markers, and the performance with one user with spreading is given by this square markers. So this set of curves we already discussed in the last tutorial, and we had seen that spreading helps us combat multipath due to the autocorrelation properties of the spreading code. So it gives us a better performance with spreading as compared to without spreading. Please note that BPSK without spreading has been carried out for a single user. So the comparison was already discussed in the last tutorial, but now our interest is to see what happens in the multi-user scenario. And as we see, there is a performance degradation when the number of users increase. The BER performance degrades and is poor when we have a BPSK with a spreading code of with 3 number of users. So this of course has been done for a length code length of 4. You could experiment with higher code lengths, higher multipath numbers by varying the power delay profile parameters, etc., and you could see how the system behaves. But I would like to make 2 very important points over here, and the first point is that this performance evaluation has been done for downlink with uniform power allocation or equal power allocation for all the users. So we basically had split the total transmit power into 3 components, in this case equal components, and we had assigned that power to each user. So this was a simplistic assumption that we had made. Downlink is important because performance evaluation in the uplink will be more challenging. The reason is because usually we need to come up with a power allocation scheme which is optimum for uplink. We may not use a uniform power allocation scheme for uplink because the users may be distributed in terms of proximity from the base station at different locations. So certain users may be closer to the base station and some users may be at a distance, in which case in the uplink the users close to the base station, if we assign equal power to all the users, then users close to the base station will act as strong interferers to users which are at a faraway distance from the base station, and as such what happens is that the performance for different users will vary, and users far away from the base station will see a very significant performance degradation. So in that case we will have to come up with some kind of power allocation scheme depending on the location of the users. In essence, what I am trying to talk about is the near far effect that needs to be taken into account before allocating power, and so the uplink problem to start with becomes more challenging than the downlink problem. Our evaluation is for downlink, and another very important assumption that we have made is regarding synchronization of the received signal with the codes that we are trying to correlate the received signal with. So we have assumed this to be perfect. So in actual situations, in reality, there will be some loss in synchronization inevitably, and now it depends upon the correlation properties of the code as to how this will manifest in BER degradation. The reason why I am making these 2 points is because the performance that we see over here is due to these assumptions is a very optimistic view of things, but generally the performance of this multi-user DSSS BPSK system may be worse than what is shown over here if we relax these assumptions and we have models in order to incorporate synchronization, offset errors, timing offset errors, etc. And also if we try and repeat this exercise for uplink by considering near far effect and so on and so forth. So this concludes the tutorial for multi-user DSSS BPSK system over a relay fading channel with MMSE equalization. I thank you.